Electric Field Part 2. Now we're going to determine the electric field created by a point charge Q. Let's take Q positive. All point charges create in their vicinity an electric field E. But we don't know its characteristics, its line of action, direction, its magnitude. How to determine the characteristics of the electric field E? The point charge Q, all point charges create in their vicinity an electric field. This charge will create an electric field in its vicinity. Let's place a point charge at a point A. Let's call the point charge Q and let it be positive. We notice that there is a repulsion between the two charges because they have the same sign. We're going to draw the repulsion between them. This is the repulsion force F. Going back to that expression, the charge Q creates in its vicinity an electric field E. So when we place another charge at a point A, it is subjected to a force F equals to Q times E, as in this case. F equals to QE. So let's determine the direction of the electric field E. F and E are proportional vectors, but Q is positive, so F and E have the same direction. So the electric field created by Q at point A has this direction. Let's take another example. The same point charge, Q, which is also positive, creates in its vicinity an electric field E. If we place at a point A point charge, Q, but negative in this case, these two charges will attract each other by an electric force. So Q attracts small q by an electric force F. The charge Q creates an electric field E. So the charge small q will be subjected to an electric force F, which is equal to QE. Q is negative, so F and E have opposite directions. So we draw the electric field at A in this direction, which opposes the force F. What do we notice? Let's place another charge, Q negative, here. The electric field at this point will also be directed in this way. Why? Because the force created by the big charge Q on the small charge Q is an attraction force, and F equals to QE, so F and E have opposite directions. Let's place a point charge here, Q, which is positive. These two charges have the same sign, so they will repel. Big Q will repel small q. Now since F equals to QE and Q is positive, so the electric field has the same direction as F. So if the charge is positive, on all points in its vicinity, it will create an electric field that is directed radially outward. this electric field created by the charge Q will be radiated outward. The charge Q creates in its vicinity an electric field that is radially outward. And it is independent of the charges that we place in its vicinity. Always Q will create in its vicinity an electric field that is radially outward. Now, in the case where the point charge Q is negative, it will create in its vicinity an electric field E. Let's place in its vicinity a point charge Q positive. This charge will be attracted by the bigger charge Q. So it will be subjected to a force F, an attraction force directed towards big Q. On the other hand, Q is found in the electric field E created by the big charge Q. Hence, it is subjected to an electric force F equals to QE. But Q is positive, and as a result, the electric field has the same direction as F. Since these are proportional vectors and the concept of proportionality is positive, so F and E have the same direction, and this is E. If we place at another point another charge Q, which is also positive, we notice that also small q is subjected to an electric field E in this way. If we place in the vicinity of a negative charge Q another charge Q, which is also negative, these two charges will repel. We draw the repulsion force in this direction. Now, since small q is found in the electric field of the big charge Q, it is subjected to an electric force F given by Q times E. But Q is negative, and as a result, F and E will have opposite directions. What do we notice? We notice that the charge Q, which is negative, creates in its vicinity an electric field that is directed radially inwards, that is directed towards it. Therefore, the charge Q, which is negative, creates in its vicinity an electric field. In which direction? It is always directed towards the charge Q. When the charge is positive, it will create in its vicinity an electric field that will be radiated outward. We now determine the line of action, the direction. Now we have to determine the magnitude of this electric field. We always have that the electric field is directed towards the center of the point charge from the point that we're considering. So the line of action of this field is the line joining the center of the charge and the point that is considered. So how can we determine the magnitude of the electric field? According to Coulomb's law, 2 point charges, Q and Q, that are separated by a distance d, will interact by an electric force F, which is equal to KQQ over d squared. This expression is similar to the force of gravitation, but we replace the masses by the charges, because the charges are responsible for the electric force. There, the masses were responsible for the gravitational force. In the law of gravitation, G was the constant of gravitation. Here we call it Coulomb's constant, which is equal to 9 times 10 exponent 9 in the SI, in vacuum. According to Coulomb's law, 2-point charges placed at a distance d, each will be subjected to an electric force F given by this expression. So how can we use this expression to determine the magnitude of the electric field? Big Q will create on small q this force. Small q is found inside the electric field of big Q. So we write F equals to Q times E. Q will create an electric field in its vicinity, and as a result, when we place another charge, small q, in the field of big Q, small q will be subjected to a force F equals to QE. Its magnitude is equal to absolute value of Q times E, since the charge Q can be negative. So as magnitudes are positive, we have to put an absolute value because the force has to be positive all the time. So when comparing these two expressions, we get QE equals to Q over D squared. By simplifying Q, we get that E equals to K big Q over D squared. Q is an absolute value. This is the magnitude of the electric field created by the big charge Q on this point at a distance d from it. A charge Q that is positive, for example, creates at a point M an electric field E that is directed outward. A positive charge creates an electric field that is directed outwards. That is the distance d. Now for a negative charge, it will create at a certain point in its vicinity an electric field E that is directed towards the negative charge. What is the magnitude of the electric field? It is equal to K Q over D squared. The electric field is independent of the charges that are placed in the vicinity of the big charge. The electric field is a characteristic of the charge that creates it. And as we move away from the point charge, D increases, and so E will decrease. Moreover, the electric field vector E is a characteristic of Q. What does it mean by characteristics? The characteristics of a vector are its line of action, direction, and magnitude. They only depend on Q. They are determined by Q. This is the magnitude. If Q is positive, E is directed outwards. If Q is negative, E is directed inwards. Now, what unit do we use for the magnitude of the electric field? The force vector F acting on a point charge Q that is under an electric field E is given by F equals to QE. The magnitude of F is the absolute value of Q multiplied by E. F is in newtons, since it's a force. The charge Q is in coulombs, and as a result, E is in newtons per coulomb. Newton per Coulomb is not the unit that is used in the international system for the electric field. It is the volt per meter. So how can we prove that the Newton per Coulomb is the volt per meter? We know that the electric energy consumed by a dipole is given by U times I times T. U is the electric voltage of the dipole, I is the electric current, and T is the duration of the consumption. On the other hand, we know that the electric current is given by Q over T. Q is the amount of the electric charge that traverses the dipole during a certain time t. As a result, Q equals to I times T. So we can write that the energy is equal to U times Q. What is the unit of the energy in the international system? It is the joule. U is in volts and the charge is in coulombs. Then a 1 joule is equal to 1 volts multiplied by 1 coulombs. The work of a force is given by the force multiplied by the displacement. Thus, the joule is equivalent to the Newton multiplied by meter. So 1 joule is equivalent to 1 Newton multiplied by 1 meters. So by equating both expressions, we obtain 1 Newton times 1 meters equals to 1 volt multiplied by 1 coulomb. As a result, Newton per coulomb, if we divide by a coulomb, is equal to volt per meter. So we arrive at the unit that is used for the magnitude of the electric field in the international system, which is the volt per meter. Now we're going to consider an application to find and draw the magnitude of the electric field created by a point charge Q equals to 8 times 10 exponent minus 4 coulomb at points A at 4 meters and B at 6 meters from the point charge Q. The magnitude of the electric field created by Q at A is given by K multiplied by Q in absolute value over the square of the distance between Q and A, which is OA squared. K is a constant, 9 times 10 exponent 9. The absolute value of Q is equal to 8 multiplied by 10 exponent minus 9 over 4 times 10 exponent minus 2 squared. (28,125 volts per meter). This is the magnitude of the electric field created by Q at point A. Let's draw it now without respecting any scale. The origin of this field is point A. The direction of this field is either outward or inward. This is EA, and this is the other possibility of the electric field. So which one of these two directions is the correct representation? Note that Q is positive. Then the electric field created by it is oriented outward. It moves away from the charge. So the true direction is the one above. Now, the electric field created by Q at B. the electric field created by Q on B is equal to K, absolute value of Q, over the square of the distance between the charge and B, which is OB squared. K is equal to 9 times 10 exponent 9 multiplied by 5 times 10 exponent minus 9 over the square of the distance. $12,500 volts per meter, and this is the magnitude of the electric field at point B. The origin of this field is B. The direction is either towards O or away from O. The line of action of this field is the line OB. So the charge has a positive sign, so the electric field is directed outward, is directed away from the point charge. So the correct one is the one below. In the other application, we want to determine the electric field created by a charge Q prime on point M and N. M is at 5 centimeters and N is at 8 centimeters. The magnitude of the electric field at point M is equal to K multiplied by the absolute value of Q prime over the distance OM squared. K is equal to 9 times 10 exponent 9. Q prime is minus 10 exponent minus 8. The distance is 5 times 10 exponent minus 2 squared. The result is 36,000 volts per meter. This is the magnitude of the electric field at point M created by point charge Q prime. So to represent the electric field created by Q prime on M, the origin of this electric field is point M. The line of action is OM. It is either directed towards charge Q prime or away from charge Q prime. Which vector is the correct one? The sign of the charge Q prime is negative. So the electric field is directed towards Q prime, and therefore the correct one is the one below here. Now in the same manner, the magnitude of the electric field created by Q prime on N is given by K, absolute value of Q prime, over the distance squared. 9 times 10 exponent 9 multiplied by the absolute value of minus 10 exponent minus 8 over the distance squared, which is 8 times 10 exponent minus 2 squared. The result is 14,062.5 volts per meter. This is the magnitude of the electric field created by Q prime on N. To draw the vector of the electric field, its origin is N, the line of action is OM, Q prime is negative, then the electric field is directed towards the charge Q prime. This is E at N. The negative charge creates an electric field that is directed towards it, whereas the positive charge creates an electric field that is directed away from the charge, as you see in this case.